We were looking at the rounding of a digit corresponding to the significant figures, and the concept was multiplication and division. So it says that in the measured values to be multiplied or divided, so we have to keep the least number of significant digits as n. First we have to find out. Then the product or quotient should have the same number of significant digits. Okay. So if we consider an example, say this is 1.2 into 36.72, right? So if you do in calculator, the answer comes to be 44.064. But first I need to find n in order to modify this answer, right? So what is n now? N in this case is the least number of significant digits out of the given two numbers. So first number has how much? This n value is 2. Second number has n value equal to 4. In the sense, in my answer I should keep only 2. That's why it is n is 2. I should keep only 2 significant digits, right? Though I approximate this to 44.1, right, maybe, but you see that 44.1, the 0.1 cannot be written now because significant digits are only 2. I should retain only 2 significant digits. So 44 is the expected answer. Okay, so very similar to this, let's do the another example. This is 1101 divided by 10.2. Okay, so when you perform this operation, we are going to get 107.9411. Okay, but I check out of the two numbers given, 1101 and 10.2, right? I have the least value of significant digits, that is n is equal to 3, that is for 10.2. Okay, so 10.2 has n equal to 3. I should have only 3 digits in my answer. So how do you convert this into a 3-digit number? I can see after dot 9 I have, right? I don't want any other values. So 107.9 we will consider and convert 9 into the, right? Since this is the cutoff digit, next digit is greater than 5, so this has to be increased. So this implies 108 is your answer. Okay, so 107.94 is accurate answer, 108 is the right approximated answer by using the significant digits. All right, that's all. Next is called the error analysis. So we know that, right, we can use several instruments in physics to measure several quantities. Okay, but no one is perfect, right? So no machine is also perfect, there is an error. So this means each and every instrument that we use to measure, right, some quantity, there will be up to some accuracy, right? There is an accuracy value, right? That value is what we call as a least possible count, right? Initially we took an example, correct? So that it's related to that. So we can say every instrument can measure up to a certain accuracy. So that accuracy is called as the least count. Okay, so short form LC. Right. What is the least possible count? Right, we have different standard values for different instruments. Maybe let's say we are using a normal scale, right? Normal scale could be using the millimeters, right? What is the least count? Least count is 1 mm, because you cannot calculate a value lesser than that, right? You cannot measure, right? So if you use the, say, vernier calipers, what is the minimum distance that you can measure? Minimum size is 0.1 mm. Okay, similarly we have other device or instrument called, say, screw gauge. This can measure up to 0.01 m. Lesser than that it is not possible, right? So other examples could be a stopwatch, right, which gives an accuracy of 0.1 seconds, right? And maybe a thermometer, right? It can give 1 degree Celsius and so on, right? We have the possible errors, right, which is because of this least count. Always we have, right, an error in the measurement of any quantity through an instrument, right? So let us say, what is the allowed error? Because of this limitation in the least count, right, we have a allowed error, in the sense that much error is fine for us whenever we measure any quantity. So now we know that there is an error, so that is error in measurement due to the limitation, that is least count itself is the limitation, right, of instrument. So this error is called as, what is called as a permissible error. You call it as a permissible error. So if you have a scale, the least count is 1 mm. So maximum permissible error measured by that particular scale, right, is 1 mm, right? Because there can be maximum error of 1 mm. Because as soon as you cross 1 mm limit, you get the next mm, that is 2 mm. So then there is no error, and so on. So maximum permissible error could be like this. Okay, so this means, for example, the maximum permissible error of uh, a scale is 1 mm, as least count itself is 1 mm. Now the point is this implies, if measured length, let's say the measured length is L equal to 26 mm. So when L is equal to 26 mm, you see that there can be an error of maximum 1 mm. So actual length could be, this implies, what is the actual length? Right? Could be, it's not the same. I'm not saying it is, there is an error. There may be an error. So actual length could be 26 minus 1 or 26 plus 1. Right? Because 1 mm is the possible error, maximum error. So that may be 25 mm, or this is equal to 27 mm. Worst cases. So we can try to write this as L is equal to 26 plus or minus 1 millimeters. All right. So let's take another example, right? So let's say there is a device, right, which which is used to measure the length. Let L is equal to, I will keep it as 24.6 millimeters. This is the measured length, and least count of that particular device, let us say this is 0.1 mm. Okay, it's a different device. Then, right, this implies what could be the range of actual L. Actual L should be 24.6 plus or minus 0.1, right? So many millimeters, right? So including the maximum possible error of the system, you are supposed to mention what could be the length. This is one of the standard way of representing the measurements. Okay, because no measurement is perfect, there will be a small amount of allowed error. So including that error, this is how you try to represent any measurement that happens using a instrument. Okay, now we understood that there will be error, right? So now we look into the types of errors. So that is classification of errors. Right. So these errors occur because of several reasons. First one may be what is the cause of error, right? Some such as systematic error and the random errors. They are called as the errors based on the cause, right? And we have another type of classification that's based on what is the magnitude of errors, right? We call it as absolute error, mean error, relative error, etc., right? So now the first type is called as the, it's a systematic error. First category. So in this case, systematic error means errors whose causes are known to us. We know what is the reason. Okay, so causes are known, right? So this means since you know the reason behind such error, the major advantage here is that can be minimized. Whatever error happens, you can try to reduce them, right? So what could be the causes? Like instrument errors due to uh, due to some problems with the instruments. Okay, you have an instrument and there is some sort of what you call error with the instrument. So we know that if there is an error such as systematic error, right, because of a problematic instrument, you can replace that particular instrument by more accurate one. Okay, that's the simplest case. So let's see the examples. We can say erroneous instruments. So when I know that instrument is not proper, I can simply replace. Okay, and maybe the systematic error may also occur if you neglect some data when you do some calculation. Okay, so certain facts are neglected. Say when we measure the period of a pendulum, right, air resistance might be neglected initially. It is not accurate. Then you think that, okay, I missed the air resistance, and now I add the air resistance to get more accurate value. So you see that it was a systematic error because you know the fact that something you are missing, and then you add it to the concept to get the accurate one, right? So maybe error is also due to the changes of the physical parameters are not being considered, such as temperature. When you started the experiment, there was a temperature, say 30 degrees, but during the process, temperature increased to 32, but you never consider that. You use only 30 throughout, because of which there could be some error. Okay, then since you know the reason, I didn't consider the temperature change, right? You will consider it later and you get a more accurate value. So that's how it works. Okay. So this kind of errors are called as systematic errors. All right. Then let's go to the second case. This is random. Random errors. Right. This means the reasons unknown. So since we don't know the reason behind these kind of errors, right, it is not possible to minimize, right? You cannot minimize because I don't know the reason. Okay, can not be minimized. So this is because the reason is not known, as there are so many number of reasons for these kind of errors. So specifically you cannot find the accurate reason, but you may guess. Okay, fine. Now let us consider a simple example, right? This is something like, let us say there is a very minute measurement that is happening in a lab. Okay, so and you are balancing certain things to find out the weight of an object, but when this uh, process is very delicate, right, even somebody is walking nearby can cause vibrations that imbalances your the weight. Okay, when the weight is say very less, the accuracy is expected, but somebody who is walking in the floor will also cause vibrations, because of which there will be an error in the measurement of weight of a very small object, right? So this implies that you don't know what it is, right? Who is causing and what happens, we are not able to guess. It's a random error, right? That's why normally when people measure gold, weight of gold, you keep it inside a box, right? So that those kind of vibrations may be minimized. You cannot eliminate, you simply minimize, right? So what is the solution for these kind of issues, right? There is no single answer to this. What you can do is, in order to minimize this kind of errors, you repeat the observations many times and take a mean. For example, my intention is to calculate the weight of an object. Okay, I measure these weights n times, right? Every time I note down and I take the average of all the readings as my final value. Okay, so repeating the measurement repeating the measurement to get large number of values and taking the mean can reduce such errors. So that means you measured something, some quantity, say length, okay, or weight. So what do, right? That value is, final value is equal to every experiment. A1, first experiment result, I measured the same weight once again 2, like that I repeat this n times. An whole divided by n gives me an average of the quantities which we measure. So this is the way how you represent the measurement whenever there is a random error possible. Okay. Next type of error is absolute. Okay, so there could be an error that is associated with the actual value of the quantity and the measured value of quantity. So if there is a difference, that difference is what is called as absolute error. Okay, so this is nothing but the difference between between the true value and the measured value. All right, so let us assume that the actual value of the measurement, the actual length is, say, I'll say am. Let am be the actual value and say a1 is the measured value. Actual value is 20 centimeters, I measured 21 centimeter possible, so a1 is that. Okay, now this means, how do you measure the, right, absolute value? It is magnitude, in the sense I can write it as delta a1. Delta a1 represents small change in a1 is nothing but the difference. I should take the difference of actual value, that is am minus a1. All right, so this is the a1, this is delta a1 represents the absolute error. So since we want to keep this positive, you can take this as the magnitude, in the sense, even if you get a different value, such as, instead of finding the bigger value I find a smaller value. 20 is measured as 90. So you see that the difference could be negative. So to eliminate the sign change, you take a magnitude. So magnitude is denoted by two lines at the end. So this means the answer is always positive. Okay, then we go for mean absolute. This is mean absolute error. So here, very similar, we repeat the experiment many times. We measure the same quantity again and again, and we keep calculating the absolute error of every other quantities, such as, right? So calculate, say, delta A2, the delta A3, etc. up to delta AN by repeating the measurement n times. So repeat that. That means delta A2 will be, right? I can write magnitude of delta A2 is AM minus A2. A2 is the measurement you did for the second time. AM is the actual measurement. So keep calculating this difference. Sorry, delta A3 magnitude of delta A3 could be AM minus A3 and so on. Repeat this to get delta AN, which is AM minus AN. Then we write the mean of absolute value. We try to calculate the average value of these errors. So delta, this is delta A, its magnitude, and I'm trying to calculate the mean is equal to, so let's see this, add all the errors, that is magnitude delta A1 plus magnitude delta A2 plus dot 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 up to the last number, that is delta AN, whole divided by how many such errors we have? We have n such errors. So dividing by n is going to get a mean value of the error. This is called as mean absolute error. Okay, so this means when we have the mean absolute error like this, so the final measurement can be, this implies measurement could be, see, we got a value, this is my final value of A, this could be AM plus or minus this delta A mean. It's obvious because the absolute value of the error is delta, so this could be plus delta or minus delta. So because of which we write it in the same format which we discussed earlier. When you have a error in the measurement by an equipment, you perform plus or minus of that value with your measured value. Okay, so which means the value of the quantity lies between AM minus delta A mean to AM plus delta A mean. Somewhere in the middle, the value exists. Okay, now let's proceed further. The next one is, it's called as relative, or it's called as fractional. Relative or fractional error. Okay, so let's try to uh, relate the concept of relative error to the previous errors. Now if you try to take the error of mean we try to take a ratio. Okay, so this is the ratio of the mean absolute error to the mean of the quantity measured, right? So this ratio is called as relative error. Okay, is called relative or the fractional error. So this can be defined like relative error is equal to, so you see the notation which we used earlier is delta A mean whole divided by, this is AM. Okay, if you want to write this in percentage, so that is percentage relative error. Sometimes we need this because question says calculate relative error in percentage, then this becomes the same delta A mean divided by AM into 100. Okay, so these are the various types of errors that are possible. Okay, now let's go to a problem. Let's solve a simple problem that discuss that using which we understand all concepts like what is a systematic, what is random, what is absolute, what is mean, absolute, and what is a relative. Okay, the question is like this. The diameter of a wire is measured by a screw gauge was 2.620, 2.625, 2.630, 2.628, and 2.626 centimeters. Okay, so calculate part A of the question is mean value of diameter. Part B of the question, absolute error of each measurement. Part C of the question, mean absolute error. Then part D of the question is fractional error. Then E is percentage error. Okay, so this is the question. So you can see that there has been 5 different measurements, right? So let us try to write this. So part A answer is mean value of the diameter. So this is nothing but AM. So let's assume all these values are A1, A2, A3, etc. Right? So 5 times we have measured. So A1, A2, A3, A4, A5. So it is nothing but A1 plus A2 plus A3 plus A4 plus A5 whole divided by 5. So this is 2.620 plus this is 2.625, right, plus this is 2.630 plus 2.628, 2.626 whole divided by 5 comes to be 2.626, 2.626 centimeters. Okay, now this is the answer to A. Then part B is absolute error of every measurement, right? Every measurement, in a sense, I need to find the delta A values. So how do you measure? This is delta A1 is nothing but the mean value, that is 2.626 minus the measured value, that is 2.620, right? So from where you are getting this, I am considering the mean. This is AM and this is A1. So AM minus A1 is delta A1. Okay, so we have applied the same rule here to measure this. So this is equal to, so this is a positive quantity and 0.006, okay, centimeters. This is the error. It is positive. Okay, so there can be a positive or negative that might come. So delta A2 is equal to same 2.626 minus the measured value, which is 2.625. Correct? So this is 0.001 centimeter. Similarly, delta A3 is equal to, we have the value of average mean value 2.626 minus the value which we got is 2.630. So this is minus 0.004 centimeter. Keep the minus as it is, no problem. Okay, then delta A4 is 2.626 minus 2.628 is the measured one. So you can see this is minus 0.002 centimeters. So absolute error of the fifth measurement A5, delta A5 is 2.626 minus 2.626, so 0. Okay, this is part B. Then we'll go to part C of the question. It says that mean absolute error. So mean absolute error is delta A mean. So how do you measure that? Take the magnitude. So magnitude of delta A1 plus magnitude of delta A2 plus the magnitude of delta A3 plus A4 plus delta A5 whole divided by 5. Right? You see that we neglect the sign here. Even if it is a negative, you are going to write it as a positive. Okay, so first term is plus 0.006 remains as it is. Second is also positive, so 001. You see the third one, it is actually negative, but we are writing a positive here because of this being a magnitude term. Okay, only consider magnitude, no sign. So plus 0.004 plus 0.002 plus 0 whole divided by 5. So this becomes 0.003. Okay, then the part D of the question, it says that fractional error. So how do you measure fractional error? That is nothing but it can be positive or negative. So you see this is delta A mean divided by the AM. So that is always plus or minus delta A mean is 0.003 divided by this is 2.626. So this means this is equal to plus or minus 0.001. So remember, in all the cases we are retaining 3 decimal places only, right? So even if you get a value other than this, you approximate, right, to 3 decimal places. Okay, then part E of the question, it says percentage error. This could be whatever value we got as a fractional error, that is plus or minus 0.001, should be multiplied with by 100. Okay, so this is plus or minus 0.1 percentage of error. Okay, so you see that the whole diameter of the wire which is measured, now you can represent, this is not a part of the question, but still I'm trying to give a different view. This is 2.626 is the mean, plus or minus 0.1%, you can write like this, so many centimeters. Okay, 0.626 plus or minus 0.1%. 0.1% in the sense you want to convert this into the actual value, means you divide by 100, because we multiplied by 100 to get a percentage. So you divide by 100 to get the required answer. Okay, so the various types of errors have been completed in today's class.